Hello everyone, welcome to yet another lecture series on basics of electrical engineering. In this video, we are going to talk about root mean square value, also referred to as RMS value. So let's get started. So root mean square value. In order to understand this term better, let us have few examples of what it is all about, and then probably get into the actual definition of root mean square value. So let us consider a DC source. When it is connected to a resistor, the current flows in this form where we are assuming a current of 10 amps. So for a direct current, the constant current remains constant throughout the process. So if you are supposed to like find out the power at any instant of time, it will always be equal to P is equal to Vi. So we know the value of I. If we know the value of V, the value of P will be constant throughout the instant at any point of time. If you are having an AC source connected to a resistor, then the nature of waveform will be sinusoidal in nature with respect to current. So if you are supposed to find out the power at any instant, say at this point the current is 2 amps. So if you find the power, it will be different. Again, if you find the power at this instant where the current is 5 amps, the power will be different. And if you are supposed to find the value of power at this instant for a current of 10 amps, so what I'm trying to say is the power keeps on changing at every instant of time. And in order to have a generalized perception for analyzing any such circuits in with respect to AC, there was a concept called as root mean square value that was introduced. So what is root mean square value? If you're considering a waveform and you're supposed to have its effective value is to be found out, then I1 is the current flowing with respect to T1, I2 is the current flowing to with respect to T2, and I3 is the current flowing with respect to T3. Then the effective RMS value is given as that is nothing but the abbreviation of RMS value, that is root mean square. So root of the mean values of the square of the individual terms. So that is RMS value. So if you see, the root of the entire term is taken into consideration. The mean value, that is nothing but mean value of each and every current that is associated, whole divided by the overall mean value. So number of instants, if there are three values that are considered, you will be dividing it by 3. So square of these values, so that is RMS value. You can also represent it in integration form, because integration is basically the summation of all these values that are there. So that's the reason why we will be representing it in this form. So generally, in order to arrive at a common conclusion, the current is measured by the amount of work done, or the amount of heat it will produce, isn't it? So the RMS value of alternating current is basically defined as the steady current which will do the same amount of work in the same time, or would produce the same heating effect as when alternating current is applied for the same time. That means for this DC circuit that you have a resistor connected to a DC source will have the same amount of heating effect with respect to AC, and that can be measured by this method that is called as root mean square value. So it is measured in terms of the amount of heat that is produced. So remember this important point with respect to RMS value. However, the process involved in order to find out the RMS value is basically by applying this formula, and we know the purpose of RMS value, isn't it? So if you are supposed to find the value of power at any instant, you can directly find out, rather than in a DC it remains constant, but in AC it keeps on changing. In order to have an effective value, we'll be finding out the RMS value. So once this point is clear, we'll be finding out how to find, like, calculate the value of RMS value for a sinusoidal waveform. So let us consider a sinusoidal waveform whose value has been given by V is equal to Vm sine theta for a duration of 0 to 2 pi, that is one complete cycle. So according to our previous relation IRMS, we have found out the formula for RMS value, isn't it? So we'll be applying the same, the although it's for current, we can apply the same value for voltages and power as well. So with respect to voltage, we are considering one complete cycle, so we are writing it in terms of 1 by 2 pi. And T1 here is starts, the waveform starts from 0 and it ends at T2, that is nothing but 2 pi over here. So V square theta d theta, because V is the magnitude of voltage that we are considering, square of its value according to the formula, and d theta, it is with respect to d theta, because of the y axis is in terms of theta. So that can be further simplified as V value is written as Vm sin theta and we have substituted it. So further Vm square is taken out in common, and sine square theta can be written as 1 minus cos 2 theta by 2. I have substituted that. So once that is done, we will be applying integration of half is nothing but theta by 2, and integration of cos 2 theta is sine 2 theta whole divided by 2. So you will be getting substituting and simplifying, you will be getting it in this form. So for the simplification, substituting upper and lower limits in this formula, you will be getting Vm square by 2, square root of Vm square by 2, and taking Vm common, you will be getting Vm by root 2. So the effective value of RMS value of a sinusoidal waveform is 0.707 Vm. So similar analysis can be applied for different types of waveforms such as triangular or square wave. However, the values that you get will be differing only with respect to the result that you're getting. So you can try the approach for all the other waveforms as well. If you have any questions, please feel free to reach out with any questions and concerns you may have. Thanks for watching this video.